So we now want to study things in the case that D is very, very much less than R. Okay? So let's first of all think about the mod of R plus. What is the mod of R plus equal to? Square root of R plus dot R plus, right? So R plus dot R plus will be R dot R minus D dot R plus D dot D over 4. Okay? And mod of R dot R is R squared, so I can take R squared out. And I'm left with 1 minus D dot R over R squared plus this term is going to be very small. Okay? So I'm going to sorry?
D dot R over.
D dot R over 2? Is it?
No, that's fine.
Is it fine?
Yes.
Well, Zara, is it fine? Oh, good. That was a little test. Absolutely. We pulled out an R. Very good. Okay? Good. And now this term we will see as negligible. Okay? So I'm just going to write dot dot dot. We're not going to need to worry about that term. How can I expand the square root if this number is very small? Square root of 1 minus x when x is small is approximately equal to 1 minus x on 2. Good. So I'm going to do the same thing here. This is R into 1 minus D dot R over 2 R squared. And there's more terms there, which equals, we'll have an R minus 1R will cancel with 1R at the bottom, and we'll be left with D dot R over 2R plus dot dot dot. And there's a reason. There's a reason why we stopped here. You see, what is vector R divided by R? R hat, a unit vector. So you can see that even when we let R get very big, this term does not vanish. Okay? All of the other terms will vanish. This term remains order 1. Okay? So we can write the mod of R plus is R minus 1/2 D dot R hat. Now I can immediately plus terms that vanish. That vanish as mod of D divided by the mod of R goes to 0. So I don't need to worry about those. So I can immediately write, what will R minus be? How is R plus related to R minus? You change D into minus D. So if we just look here and we change D into minus D, what will the mod of R minus be? R plus 1/2 d dot r hat plus the terms that vanish. Okay? Okay, now I want, it's not r plus itself that I want 1 over r plus. So 1 over r plus looks like 1 over r minus 1/2 d dot r hat. And what is this equal to? Well, I can pull out an r from the denominator, and then I'm left with 1 minus d dot r hat over 2r. And what is this equal to, approximately? So this looks like this factor over here looks like 1 over 1 minus x for small x. What is that equal to? 1 over 1 minus x for small x, what is it equal to?
1 plus x.
So this is exactly, 1 over 1 minus x is exactly equal to that geometric sum, right? And if x is very small, what can you do about x squared? Very, very, very small. And we're physicists, so we just ignore those. Okay? So 1 over 1 minus x is 1 plus x. So this is equal to 1 over r into 1 plus d dot r hat over 2r, which is equal to 1 over r plus d dot r over 2r squared. Good. Okay, who can tell me what 1 over r minus is? One over r minus d dot r over 2r squared. This should
R hat.
good, very good. Yes, it should. Okay, that r hat is from there. Good. So now we've got a formula for 1 over r minus, and we've got a formula for 1 over r plus. We can plug it into our formula for v of r. So v of r equals q over 4 pi epsilon naught 1 over r plus d dot r hat over 2r squared minus q over 4 pi epsilon naught 1 over r minus d dot r hat over 2r squared. Now, if this term was not here, what would we have? The field of a point charge. Everyone happy? And if this term was not here, what would we have? Field of a point charge. Okay? Now, can you see that this first term exactly cancels against that first term? Okay? And that's what you'd expect. If you think about the electric field that this positive charge is setting up, that tries to cancel the electric field that the negative charge sets up. This positive charge is trying to push positive particles away from it. This negative charge is trying to pull positively charged particles towards it. So this field is exactly cancelling that field, or trying to, okay? They're trying to cancel. They don't cancel perfectly. Why not? Because they're not at the same position. And you can see the piece that doesn't cancel is the second one here, because here we've got a plus and then we've got a minus times a minus, which is also a plus. And the piece that doesn't cancel depends on D. So the cancellation is not perfect. These two don't cancel each other out precisely because D is non-zero. So if we sum up these terms, that term cancels against that term, and summing the remaining terms, we have Q D dot R hat over 4 pi epsilon naught to R squared. Good. So that now is the potential of a dipole. Given the potential of a dipole, what kinds of things can we do? If we have the potential of a dipole, what can we do? We can calculate the electric field. How do we calculate the electric field? Minus the gradient. Good. So I want you guys to do that now. This is a result that we're going to need. So here we have plus Q, here we have minus Q. The vector D stretches between the two of them, and I want to calculate the field at some point. Actually, I don't want to, this one we won't need. The one that I'll need is this one. Let's put the dipole like this. Plus Q, minus Q. Let's put D like that. And I want you to calculate the electric field at this point here. And what do you need to do? You need to calculate minus the gradient of V. The coordinates of this point, let's imagine that this is the x direction. The coordinates of this point is x, y is 0, z is 0. Okay? So you need to work out what is the potential and then calculate minus the gradient. Okay? Go for it. Okay guys, I think that sufficiently many of us have got it. Let's continue, and if you've got questions, make sure to go through it, to complete it later, and to ask about it, okay? But the answer that I've seen that many of you have gotten, which is correct, is this answer for the electric field. We're going to use this later, so it's a good thing to hold on to and remember. But what I would like to point out now is something pretty interesting. You see, what does this formula look like? There is 2, and now this vector D, which defines the dipole, it's the distance between the two charges multiplied by the unit vector that stretches from the minus charge to the plus charge. In this case, that unit vector is x hat. So what we have sitting here is, look at how, look at the final expression, and what I want to look at is, how does it depend on the charge of the dipole, and how does it depend on this displacement vector stretching between the two of them? Okay? That's what I would like to understand. And if we look at this here, what is happening is, this looks like 2, we've got Q, so that's one of the things that we want to track. Then we've got d times by x hat. So we've got d over 4 pi epsilon naught x cubed. So this does not depend on q and d separately. It only depends on the product, q times d. Look at the potential. The potential does not depend on q and d separately. It only depends on the product, q times d. And this is a very general thing. So what we characterize an electric dipole by is something called the electric dipole moment. So the electric dipole moment we denote by P, and P is equal to the charge of the dipole times by D. And what you will see is in all of the formulas that we derive for our dipoles, in this situation where we have assumed that the mod of D is very much less than the mod of R, everything depends not on Q and D separately, it only depends on the electric dipole moment. Okay? So that's the thing that characterizes our system. So the same way that the charge told you how strongly do you interact with an electric field, in this case when you've got a system of dipoles, the thing that tells you how strongly you interact with an electric field is the electric dipole moment. Notice also the fall off is now like 1 over r cubed, not 1 over r squared. And the reason why it looks like 1 over r cubed is that the field of the positive charge is cancelling with the field of the negative charge. So this is producing a 1 over r squared electric field. This is producing a 1 over r squared electric field. They try to cancel. They don't manage to cancel perfectly, but they do cancel partially. And the field that remains is 1 over r cubed. Okay? So that's what happens. Good. So that's the story of the electric dipole. I now want to use it to look at the typical process. So our goal is to study how does matter, maybe this wooden desk or something like that, how does it interact with an electric field? And there's one basic kind of interaction that can happen, and this is what happens when we consider matter-electric field interactions, just many copies of this one thing. And what it is, it's the interaction of a charge with something that's neutral. Why does a charge interact with a neutral atom? Can a charge interact with a neutral atom? Yes. But if the atom is neutral, does it set up a field? Good. So, the key word here is polarization. So what we're going to consider is an ion and sitting over here we have an atom. Now the atom is neutral, but just like we saw before, the electron cloud is attracted towards the ion and the positively charged nucleus is repelled from the ion. The electron cloud, of course, is the thing that moves the most. As a result, this side becomes positive and this side becomes negative. The language that we use is, we say the ion polarizes the atom. So the ion polarizes the atom, and this is the basic effect that happens when electric fields interact with matter. It's always polarization. And the second thing that we can say is the atom has an induced dipole moment. Induced because this electric field, the electric field set up by that ion, produced the electric dipole moment. As soon as you remove that ion, the atom goes back to being neutral and having no dipole moment. So we say the atom has an induced dipole moment. Okay. I'm going to tell you just an experimental fact. This is something that's observed in experiments, and it's observed to hold for many different materials. The thing that's observed is that, let's call that P, the induced dipole moment P is equal to some constant alpha called the polarizability times by the electric field. Let me just make sure I'm getting this the right way around. Good. Times the electric field. Okay, so this is, if you increase the electric field that you apply, the dipole moment of the atom gets bigger. If you don't apply any electric field, the atom doesn't have a dipole moment. Okay, so this makes sense. It holds if your field is not too big, so you don't rip your atom apart. And so alpha here would be a constant that we would measure for different materials. I want to give you an idea of how big alpha is. We're going to calculate it a bit later, estimate it at least by doing an experiment. But I'll tell you a typical value of alpha. Typical alpha is about 1 times 10 to the minus 40. I am very sure of that number for alpha because I found it on Google. Now, I would like to know how far does that outer electron shift? How far does it go? Now, just a little bit earlier I was asking you guys how far do you think the electron would shift, and you gave me an answer. How big did you say? About the size of the atom, right? Remember when we were saying how big is D? You told me, oh, about the size of the atom. Let's see if D really is that big. Okay? I'm going to pick an electric field. The electric field I'm going to pick is this one. The magnitude of the electric field will be, is it a 2 or a 3? 3 times 10 to the 6. This will be newtons per coulomb. Does anybody recognize how big that field is? Does that electric field, it might not mean anything, but it might mean something to someone. Yep?
It's the breakdown field of air.
It's the breakdown field of air. If you apply a field this big, okay, you'll start to see air conduct. So have you seen like lightning, or also you see sparks jumping across power lines or something like that? In that case, when air starts to become a conductor, and you see these lines of plasma where there's charged particles moving, you can ask, how big is that electric field? This is how big it is. Is this a big electric field? Sure. Do we expect electric fields to be this big in the problems that we study? Hopefully not, right? We don't want to be messing around with a field this big. So let's take this field and work out how big is P. Well, the magnitude of P will be alpha. So 10 to the minus 40 times by 3 times 10 to the 6. What is the magnitude of P equal to? Well, P is equal to Q times D. So it will be the charge times the magnitude of the distance. What did we say in our atoms? It's always the outer electron that moves the most, right? So what should we plug in for Q? 1.6 times 10 to the minus 19 coulombs, because that's the charge of the outer electron. Okay? So this is 1.6 times 10 to the minus 19 coulombs times by the mod of D. Let's now solve for the mod of D to find out how far does the electron cloud shift when we apply this huge electric field. Well, the mod of D is equal to 3 times 10 to the 6 times 10 to the minus 40 is 10 to the minus 34 over 1.6 times 10 to the minus 19. Okay, think like physicists. What's 3 divided by 1.6? 2. Times 10 to the minus 15 meters. How far does that outer electron shift? A fraction of the size of the nucleus. It hardly shifts at all. Okay? So it really, when you polarize an atom, you will never have the electron shifting very far. It always shifts some fraction of the nucleus, and that's it, some tiny little amount. That's why when I told you I was drawing my pictures that I was exaggerating. I'm greatly exaggerating. But if I don't exaggerate, my picture for the polarized atom will look exactly the same as the picture for the unpolarized atom, because the electron cloud shifts such a little bit. Okay? Good. So that gives us an idea of how small the shift is. And to believe this answer, you might find this amazing, but to believe this answer, it's all being driven because alpha is so small. So what we're going to do, actually maybe in the next lecture, maybe this lecture we'll see, is that experiment that I'm sure you've all done. Where you take a little piece of paper, you rub a pen in your hair, and you pick the paper up with the pen. Right? Have we all done that? Good. So you didn't know it at the time, but you were preparing for electromagnetism. We'll go back to that experiment and rethink that. And by thinking about that experiment, we will be able to estimate the size of alpha. And let's see if we get it this big. Okay? So we'll check that. Okay. What? Yep.
We use a typical alpha to be a magnitude 10 to the minus 40. We see that the shift is very small.
Yes.
Does it have anything to do also with the force between the electron
and the nucleus?
Yeah.
Yes, good, William. So you might ask, why is this number so small? Why is that polarizability so small? It's telling you the nucleus likes to hang on to its electron. If you apply an electric field and you try to take the electron away, it's tough. That atom is really holding on to its electron. It's not easy to pull it away. And that's also consistent with what we found this morning with the tapes. What fraction of atoms lost an electron? Roughly 1 in a million. It's a very rare thing for an atom to lose an electron. So here again, that small value of alpha tells you a nucleus does not like to let its electron go. So the electron shifts, but just a little bit. Okay? Good. Yep, Thomas?
Do conductors have a polarization constant?
Okay, we are going to talk about how conductors polarize. Conductors polarize in a very, very different way to how insulators polarize. So something like this tabletop, which is made out of wood, if I shine an electric field on it, all of the atoms inside there will polarize. If I shine an electric field on a conductor, you'll just get one polarization effect affecting the entire conductor. For the dielectric, you'll have a polarization of each atom. For the conductor, just the whole conductor will polarize. We'll talk about that in detail. Any other questions? Okay, good.